Here's a brain teaser for you. You're on a train rolling on a track at a constant speed with no friction, and the train is full of sand because you're building a sand castle, obviously. And then the train villains sneak onto the train and drill a hole in the bottom of the train so that the sand starts to flow out the bottom. What happens to the speed of the train? Does it speed up, slow down, or does it stay the same? Give it some thought, and we're going to answer that riddle at the end of this lesson. Hey, I'm Diana, and welcome to lesson 12 of Diana's Intro Physics class, also known as AP Physics 1 Review, also known as Physics by Diana. Today's lesson is momentum, and today's theme is royalty. Because Queen sang a song called Don't Stop Me Now, and I'm confident that they were singing about momentum. Momentum is an absolutely fundamental concept in physics for describing motion, and it's incredibly useful, and that cannot be overstated for understanding collisions, rockets, and shooting pool. So let's get to it. Mutationem motus proportionalem SAV motrici impressae et fieri secundum linam rectam quavis illa imprimitur. Either I just cast a solid spell, or that's Newton's second law. It's Newton's second law. Newton wrote his book of spells, and by spells I mean laws of motion, in Latin, even though he was English, because that's what scholars did in the 17th century. And when you translate all that Latin, there is no F equals ma, which is surprising, because that's how we are all taught Newton's second law nowadays. So his original translation reads, "The change in motion is proportional to the motive force impressed, and is made along the direction of the straight line in which that force is impressed." I hope you're impressed with my Latin. So, no F equals ma. Instead, Newton wrote his second law in terms of the topic of today's lesson, momentum, where force is proportional to a change in motion, and this quantity of motion he talked about is what we today call momentum. It's related to an object's velocity and its quantity of matter, mass. And we write it like this. So momentum equals P, and we use the letter P for momentum since M is already taken for mass. So P equals M, which is the quantity of matter, times V, the velocity. So for Newton's second law then, we get F equals delta mv over delta t. Force equals the rate of change of the mass times the velocity, and mv equals p. So if you want an equation that's closer to what Newton originally wrote for his second law, you would actually write F equals change in momentum over change in time. So as the quantity of motion, momentum equals mass times velocity. Let's get a handle on that idea with some calculations. Here's a simple problem. What would you rather have run into you? A runaway golf cart rolling down a hill with a puppy at the wheel, or a real adult-sized electric truck slowly rolling at you in the parking lot with a baby elephant in the driver's seat? It's a hard question because they're both so relatable. But I'm asking, which one will inflict more damage to you if it runs into you? So a problem like this is easiest to think about with momentum, so we need what? We need M and V. So let's say the golf cart plus the puppy has a mass of 260 kilograms. And let's say it's flying down the hill at 20 meters a second. So their momentum is their mass times their velocities. So 260 kilograms times 20 meters per second equals 5,200 kilogram meters per second. That's the units of, these are the units of momentum, kilogram meters per second. And then the electric truck plus the baby elephant, their total mass is, say, 1,950 kilograms and rolling at 1 meter per second. So the truck's momentum, mass times velocity, 1,950 kilograms times 1 meter per second. And that's just 1,950 kilogram meters per second. So boom, the golf cart, even though it's a rattly hunk of plastic with a puppy in it, and it has 7 times less mass than the truck, is still hitting you with 3 times the momentum, which sounds like 3 times less fun. I don't know. So in this problem, we were trying to get a sense for how momentum involves both mass and velocity. And here's another important thing that you want to get a sense for. Momentum is not inertia. People get this confused all the time. They describe a fast-moving object as having a lot of inertia, or they'll refer to an object that's hard to push as having a lot of momentum. And that's backwards. If you have mass, you always have inertia, whether you're moving or not. A house has inertia. But then momentum is a quantity of motion, how much motion and mass an object has. So a rolling cow, a rolling spherical cow, has a lot of momentum. A still cow has none. If you're not moving, you have zero momentum. Cement that into your brain. You always have inertia. This cow right now has inertia, but you don't always have momentum. Thank you for your cow. But if you do have momentum, that momentum comes in units of kilogram meters per second. Time to talk about units. Because let's be honest, these are not the most intuitive units, but there's a better way. So check it out. Let's rearrange our definition of momentum. So we had force equals delta P over delta T. So I'm going to bring up the delta T and write force times delta T equals delta P. So you get that a force exerted for some time will give you a change in momentum. This looks kind of like work, except that instead of delta X, we have delta T here. So the units of the left-hand side are force is newtons times time, which is seconds. The right-hand side is momentum. Newton seconds are my units of momentum. And we actually have a name for this whole concept, F delta T. It's called impulse. An impulse, a force exerted over time, will give you a change in momentum. So this simple rearrangement of F delta T equals delta P lets us understand a classic physics lab experiment. In one of my regular videos on the channel, I threw two eggs, one at a sheet and one at a wall. And you can imagine what happened, but you don't have to imagine because I'm going to show you. Roll the video. If I throw an egg, it'll get caught by something with give. But if I throw it with something with not give, so the sheet saved the egg, but how? Impulse and momentum, we'll explain. So let's compare our two situations. We have the egg thrown into the sheet versus thrown at a hard surface. In both cases, the egg has the same change in momentum. It goes from its mass times its initial velocity, which is very fast because of that strong arm, all the way down to zero. But with the sheet, it takes more time for the momentum to change. With more time, the average force must go down. Let's take a look at that. So it's same delta P in both cases. Let's look at the equation. We've got an F delta T. More time, that means the time goes up and the force must go down. So more time means a lower force. Whereas in the hard surface case, same change in momentum, but the egg goes from having all this momentum to no momentum really fast. So the change in time is really small. So look at my F delta T. The change in time is really, really small, which means that my force, my average force, must be really, really big. And that really big force is what led to the egg breaking. So this elegant concept of impulse, which is a force applied over time, allows us to understand a lot of problems, not just eggs. It explains why cars have airbags for safety, because it increases the amount of time that you're slowing down. And crumple zones in helmets or in cars, or in the fronts of cars. Remember we did all that complicated math about crumple zones in the kinematics video? Well, with impulse, we can easily see why crumple zones make helmets and cars safer. If you can change the given amount of momentum slowly over a longer period of time, then you decrease the average force. And this equation makes it safe to partake in all sorts of shenanigans, like jumping into a hayloft or a bouncy castle from a tall height, or throwing a baby, because if you catch the baby, then that's a slower change in momentum and it's safer for the child. But enough of these mundane applications. Let's talk about rockets. Yeah, we're gonna do rocket science today. Listen, humans are sending rovers and spacecraft all over the solar system to explore outer space, and that is nuts. And we're doing it by launching them on rockets. Momentum and impulse are the key concepts to explaining how these rockets work. So check it out. This is an amateur rocket launch. This rocket flew to an altitude of 739 meters. And if you're in the US, it's very possible that there are clubs launching rockets like this near you, and it is totally worth going to watch. I don't have access to anything that big, but I do have this little baby in the This is a real hobbyist rocket that works. This is the engine. It just goes boop up into the butt. So when the engine fires, this thing will go up about 300 meters into the sky, and a little parachute pops out. Boom. It's gonna be really hard to get back in. And then it floats gently back to the ground, and then you spend 20 minutes looking for it in the grass. But how does this little motor make the rocket go? Just looks like a cigar, but you definitely don't smoke this. The way that rockets work is elegantly simple and cool, and it brings us to one of the fundamental pillars of our modern understanding of the universe. Are you ready for this? Conservation of momentum. Let's do a problem to understand the conservation of momentum. So hold off on the rockets for a second. Picture me out in space with my spherical cow next to me. We're both alive and well. We're wearing spacesuits. We are not moving with respect to each other. So I've got my cow here, and there's me. So right now we're not moving with respect to each other. So the cow gets mad and pushes me, and so I go off to the right. But then Newton's third law, right? So when the cow pushes me over some time, she feels an equal and opposite force back over the same amount of time in this direction, which means that the cow and I had some F delta T, F Dianna delta T, and the cow's got some F cow delta T. So same amount of time. And when the cow pushes me over some time, she feels an equal and opposite push back. So these forces are the same, which means that the cow and I experience the same change in momentum. This is looking like some weird design. I'd wear that on a t-shirt. So are we going the same velocity after the push? Well, we have different masses. This is M Dianna. This is M cow. Different masses, so no, different velocity. For example, I weigh around 50 kilograms, and say the cow pushed me until I had a final speed of 5 meters a second, then my final momentum would be 250 kilogram meters per second. You could also write that as 250 Newton seconds. But we have the same momentum, which means that the cow, with her mass of, say, 100 kilograms, to have this product equal 250, her velocity would have to be 2.5 meters per second. So she should be shooting off to the left in the end with 2.5 meters per second. So we're going different speeds, 5 meters per second versus 2.5, which makes sense because I have about half the mass of this cow. Imaginations are very useful here. So different mass, different velocity, but the momentum is the same, 250 Newton seconds. But we need to look at this a little more carefully because before the push, our total momentum was 0. Since we weren't moving, our net momentum was 0. But once the cow kicks me, I have a momentum of 250 Newton seconds in this direction, and the cow has that same 250 Newton seconds in the other direction. We ignored the direction before because we were just focused on the change in momentum, but momentum is a vector, just like velocity. So if we pay attention to the signs and do the sum of the new total momentum, say to the right is positive, 250 Newton seconds, this is going to be a negative 250 Newton seconds. Sorry, I drew that very poorly. So now if we do the sum of the total momentum, adding these together, we get 0 Newton seconds. And that's our net momentum. So the final momentum is the same as the initial momentum. Yay! This is what we mean when we say that momentum is conserved. This is the conservation of momentum. The initial momentum of the whole system should be the same as the final momentum of the system. And it is always conserved everywhere. In all collisions, all interactions, all pushes, all pulls, the total momentum of everything involved before any interaction will be the same as the total momentum after the interaction. And that is how rockets work. So then I grab this. This little engine burns from here and shoots. I wonder if I can put it in here. Actually, woo. This little engine goes inside here and burns. And then shoots out a lot of low mass, like very light, but very high speed gas out the back. I guess out the bottom. Hopefully your rocket is going up. So it has low mass, but a lot of momentum because it's going so fast. momentum is conserved. So the rocket goes the other way, it goes up with the same change of momentum. It's magical because you have this light gas, not a lot of fuel, but it goes out so fast that it can give the rocket a massive boost. And then once a spacecraft is launched into space, conservation of momentum can help propel it there too. Right now, in low Earth orbit, at 720 kilometers up, there's a spacecraft with a big sail on it being pushed by light. It's the Light Sail 2, which was a crowdfunded project by the Planetary Society. Photons from the sun hit the sail and they transfer momentum because photons have momentum. So they transfer momentum to the spacecraft and propel it forward. So cool. Since we're talking about momentum and rockets, let's talk some numbers. So we can actually figure out the impulse or the total momentum that's transferred to this little rocket. We could cheat by looking at the motor and seeing these little numbers. So that C means that this gives you 10 Newton seconds. Or you could measure it. You'd measure the thrust, which is a force in newtons, and you'd measure that over time, and you'd get a graph like this with force or thrust on the y-axis and time on the x-axis. Take the area under this curve, and you would also get 10 Newton seconds. Compare this with the impulse of SpaceX's Falcon 9 first stage. The Falcon 9 is the SpaceX rocket that launched up and then landed back down on an autonomous spaceport drone ship, and then also the one that launched NASA astronauts to space, to the space station in 2020. So the thrust of the Falcon 9 first stage burns with something like 7,600 kilonewtons for not 1.8 seconds like the little rocket, but for about 162 seconds. So that ends up being an impulse of about 1.23 billion Newton seconds. And that's just the first stage. That is a lot of Newton seconds. Whew. So here are a couple final thoughts about momentum and the relation to rockets. So if you've ever shot water out of a hose, which you probably have, when you first turn on the hose, you can feel that kickback. And what you're feeling is the water being pushed out the front, which because of conservation of momentum, pushes the hose back. So if you hold a hose lightly in your hand, like just rest it there instead of holding it, and you turn on the water, the hose might actually shoot out of your hand. That's why sometimes you see the hose like wiggling around like a snake, because of conservation momentum. And another really cool little demo is something called the Leidenfrost effect. So if you drop water, regular water, onto a really hot pan, it has this unusual, weird dancing motion that the water droplets do. And the reason that's happening is because water is boiling really fast off the bottom of the droplet and creating this cushion of vapor. So you got your droplet of water, and it's shooting vapor off the bottom, which pushes the droplet upwards because of conservation of momentum. Vapor goes down, droplet goes up. Conservation of momentum, and it goes up and it bounces back down a little bit, and you get this little like very small bounces of the droplet that keep it floating almost like a hovercraft over the surface of the pan. It's really cool. And that's about it for the problems and the relation to real life. And now we can finally answer the brain teaser from the beginning of this video. So remember, I'm gonna get rid of these in case I wanna draw anything. So remember, you're on a train and you're dropping sand out of the bottom. So does the train speed up, slow down, or stay the same velocity? Think about conservation of momentum. The initial momentum must equal the final momentum. So mv initial must equal mv final. And the train is losing mass. So this mass is going down, so then the velocity must be going up, right? Wrong. I'm messing with you. Because yes, the sand is leaving the train, but the sand is still moving with the train. So it still has the same velocity, and the total momentum of the sand train system remains constant. So this equation would look a little bit more like m train final plus m sand v final, where v final equals v initial. So your mass is actually staying the same. There you go. But wait, what about after the sand hits the ground? The sand stops, but conservation momentum is still real, so the Earth must have sped up a little bit. But if the Earth sped up, then the train is now moving a little bit slower with respect to the Earth. So maybe the train does slow down just a little bit after all. Tricksy. Okay, so that's lesson 12 on momentum. When they ask what you learned on YouTube today, here are your 2 key takeaways. A change in momentum is called impulse. Delta P equals F delta T. And number 2, the total momentum of a system never changes. Never, not ever. Momentum is conserved. And here are the problems that we worked on today. Do them, or else. No, but really, that's the only way and the best way to learn physics. Now here's some fun little extra physics. For objects that are really, really, really small, and I'm talking quantum mechanical objects like atoms, electrons, ions, for them, the concept of momentum and motion gets really strange. You may have heard of Heisenberg's uncertainty principle, where you can't know an object's position, you can't know where it is, and its momentum, you can't know how massive and fast it is, at the same time with extreme precision. So that means if you know almost exactly where the object is, then you cannot know how fast it's going, and vice versa. If you know really, really well, with a lot of precision, how fast it's going, then you have very little idea where it is. And that's quantum mechanics. It is very bizarre, but it is the universe we live in. And if you continue on with physics and take a class in quantum mechanics, you get to learn a lot more of that very strange behavior. I do hope you continue with physics. And now, a message from a special guest.
Hi everyone, I'm Cheyenne. I'm an astrophysicist from St. Lucia, and I hear you doing an intro physics class. I'm so excited for you because I have absolutely loved learning about physics, and I'm so happy that you get to unravel some of the mysteries of the universe too. I'm just here to say good luck, and I wish you all the best in your studies. Bye!